Okay.
Okay, so we're gonna start at concentration. So by increasing concentration, as we already discussed, I do not mean increasing the amount of reactants, okay? Because we're just going to affect the rate, not the amount of product produced. So,
Yes. So
rate,
we will be using the same number of moles in a smaller volume,
yeah,
right? So the number of moles would stay the same, and therefore the number of moles of product would stay the same, but we just decrease the volume and therefore we increase the concentration. Why did we do that? Because we just wanted to study the effect of increasing the concentration on the rate of reaction by keeping all the rest of the factors constant. Okay. Okay.
and so a rate is something done, is how fast something is done. So over here we're talking about the rate of the reaction. So over here it is the amount of reaction done and the time it took. Okay, so the less the time taken is, the faster the rate of the reaction is. Okay, so concentration is um, concentration is the amount of, like if you're talking about solutions, it is the amount of solute per given volume of the solvent, right? So if I'm talking about salt solution, if I say that this solution is 24 mole per dm cube, if I take 1 dm cube from this salt solution, glass of salt solution, I'm going to find 24 moles in it, in this 1 dm cube, right? So this is going to be my concentration. Basically, it's just like the idea of packing a lot of molecules into a smaller space. Okay, so there are more molecules in a less space, right? In less volume. So increased concentration means that if I have 24, if I have 24 moles in 1 dm cube, and 20, and I have another glass beside this one, and I have 24 moles in 2 dm cube, this is going to be more concentrated because it's in a less volume compared to the other one, right?
Yeah,
So
it's in half of that volume. Yes.
yeah, so that's why they're going to collide more often. So they're going to be more successful collisions, and that's why we're going to have a faster rate of reaction. So all of the reaction is going to be done in a less time. Because over here, if you look at this graph, this is the x-axis, this is the y-axis. On the y-axis, I have the mass. I have time taken in seconds. So if this is my reaction A and reaction B, and this is with um, le less concentrated, this is more concentrated. Okay, let's talk about magnesium and hydrochloric acid. Okay, so I'm going to notice that the reaction finished faster in the highly concentrated acid, with the highly concentrated acid, and with the less concentrated acid, I had more time taken, right? So
With dilute acid, you have a slower reaction, so it took longer to finish.
yeah,
Took longer to complete. Right.
okay. So
So, but the total number of moles of reactions was the same because we
it
did
stays
not
the
change
same.
the number of moles. We only decreased the volume, or maybe we halvened the volume, and therefore the concentration. So, what happens when we decrease the volume? Now we are cramming up the molecules into a smaller space, and therefore they are colliding. They're all the time in random constant motion, and they're colliding with each other. And so the frequency of collisions increases and the number of successful collisions increases. What do I mean by successful collision? Yes, Sundus, tell me, what do I mean by successful collision?
So the number of collisions which result in a reaction.
Collision resulting in a product,
Yeah,
right?
yeah.
A collision resulting in a product. that is called a successful collision. Can also be called as fruitful collision, okay? So more fruitful collisions, more successful collisions mean more reactant molecules ending up to form the product. And therefore you have more product formed in a shorter time. And so the rate of reaction increases. So it only makes sense. Okay. So you should be able to explain the effect of concentration on the rate of reaction using the kinetic theory of matter. Okay. And this is all kinetic theory of matter in terms of the number of collisions. So your sequence should be more moles squeezed up in a small space, increased frequency of the number of collisions, more fruitful collisions, more product formed in a shorter interval of time, and therefore rate of reaction increased. Okay, these 4 points. Okay, move on.
So, concentration affects the rate of reaction. Okay, and then we have um, temperature. Okay, yeah. So, for concentration, there's also an experiment to prove that concentration affects the rate of reaction. Uh, and so there are two types of experiments. So you can also look at one experiment and see how it progresses, right? And another experiment in which we compare the results, right? So for this one, this is the first one, and this is between magnesium and hydrochloric acid to give us magnesium chloride and hydrogen. So as the reaction progresses, more of the reactants turn into products, and so the concentration of reactants decreases. And since this is just a one-way reaction, which means that only magnesium and hydrochloric acid can react together to give us magnesium chloride and hydrogen, and not the other way around. So this is just going in this direction, just in the forward direction. Uh, that's why when the concentration of the reactants decreases, the reaction slows down. That's how the reaction stops. So over here, you can see that the gradient is the steepest, and then as the reaction moves on in time, you can see it became less steep, and then even more so, and then there was no gradient, right? Because all the reactant got used up, and all of it was turned into the product. So this is one way you can, the fact that reactions stop when there's not enough reactants. Uh, this is a proof in itself that concentration affects the rate of reaction. Then there's another.
Okay, I hope that everybody understands that a flat horizontal line, can you please keep the graph back? A flat horizontal line parallel to the x-axis means zero gradient. Okay,
Because
I hope.
gradient is rise over run.
Right, y-axis divided by the x-axis, right? So y-axis is not changing, so the change in y-axis is zero. So zero divided by anything is zero. Okay, so that's why the gradient is zero in case of the horizontal line. I hope you guys are understanding. If there is any confusion, please raise your hand and I will then explain in detail. But I hope you understand that this horizontal line means that the gradient is zero. Okay, so what's the point behind this graph? What was the point that Sundus tried to make here? Can anybody recap? What was the point that she made just now? Yes, Ibrahim, very good. Yes?
That when the concentration decreases, the rate of reaction decreases. And
Yeah. Yes. So as the reaction is progressing, as the reaction is proceeding, what's happening?
the concentration is being lo- is reduced
Of what? Of the reactants or the
of
products?
the reactants
Very good. Yes, very good. Why? Because they are reacting to
being
form the
used.
product.
Yes, being reacted. Yes.
Yeah, they're being used up, right? Very good. So as the very good, Ibrahim. Okay, so as the reactants are getting used up, their concentration is decreasing, meaning the number of moles available per unit volume is decreasing, and therefore less collisions, and therefore the rate of reaction. So less molecules are available for reaction with the passage of time, and so the rate is decreasing. Okay, okay, move on, Sundus.
Okay. So the
So
other
much, so much so that at the end it's absolutely zero, no molecules available.
then we have another experiment over here. Okay, so, and it's between again magnesium and hydrochloric acid, but this time we're going to compare the results between two different sorts. So we're going to, because this is for concentration, we're going to use dilute hydrochloric acid and concentrated hydrochloric acid. So this is the apparatus. We're going to use a flask, and which is separated, okay, which has a separation. Um, Magnesium ribbon on one side and excess dilute hydrochloric acid on this one. So first I'm going to be using dilute, then a bung, and whenever a metal reacts with acid, hydrogen gas is produced, right? So I have a capillary tube attaching this gas being produced to the gas syringe, and this gas syringe is.
Sundus, this is not a capillary tube, this is a delivery tube.
Oh, I'm
Okay.
so sorry.
Yeah, a capillary tube is very, very thin.
Yeah, I'm so
That's
sorry.
why. Yeah, it's okay. Okay.
Okay, so
Okay. What's the purpose of separating the acid from magnesium? What's the purpose? Can anybody tell me? Why did we separate the acid from the magnesium ribbon at the start of the experiment? Can anybody guess? It's easy. Yes, yes, Nabil.
so
Yes,
that they
Nabil.
so that they will not react when they get into the gas syringe.
I didn't understand your answer. I mean, what should not react before entering the gas syringe? Yes, I
So,
think you know the idea, but you,
so that we can get the hydrogen gas separately.
no, beta. Yes, Ibrahim, you want to try?
Yes, because when we put the if we first we put if we do not separate it, when we'll put the hydrogen and when we'll put the magnesium in, so there will be no bunk because we have to put the magnesium in by ourselves. So the it will react very quickly, so the hydrogen will release out. We will not get an accurate answer then.
Yes, very good. But say it in a better way. Say that, if we don't separate them, they will start reacting before we can record the time.
Yes.
Okay, remember we have to record the time for the x-axis of our graph, right? The x-axis of our graph is time. So we should be very accurate regarding the time the reaction took, because that's how we will decide if the rate of reaction is fast or slow or whatever it is. So can you see the stopwatch? We will start the stopwatch as soon as we will remove this separation. So we will start the stopwatch as soon as the reaction begins, as soon as the reactants come into contact with each other. Yes. Okay. Otherwise, they will start reacting before we can even start recording the time. Okay, Sundus, start.
and Nabil and
Continue.
Ibrahim, do you have a question? Okay.
Yeah. Okay. Okay. Continue.
So the gas syringe is also designed to uh, what do you call it? Collect gas. Okay, that's why it has ball bearings on the side of the plunger, so that when the gas enters, it applies a pressure onto the plunger and it moves. And the glass is also scaled so that we can read. And then we have a stopwatch, so that as soon as they start reacting, as soon as we start seeing the bubbling, we start recording the time it takes
Yeah,
for the.
the ball bearings is so that the plunger does not get stuck, and to reduce friction and to increase the sensitivity. So even a minor increase in the volume of gas would push the plunger out. And so we can detect even minor increases in hydrogen production. Okay, this is to increase the sensitivity. Otherwise, hydrogen pressure has to be really high for the plunger to be pushed out. Okay, to decrease that friction, they use the ball bearing. Okay. Okay. Yes,
And
Sandus.
so first we're going to use dilute hydrochloric acid, and then we're going to do the same experiment, repeat the same experiment with concentrated hydrochloric acid, and then we're going to plot the results onto a graph. Okay, so on that graph we're going to have time as the x-axis, and volume of hydrogen produced as the y-axis. And we're going to plot all our readings. So we're going to choose a time interval, so let's say like a minute, and every minute we're going to see how what was the volume of hydrogen, and then we plot it like that.
Yeah,
So
the graph is figure 7.18 on page
yeah.
185. And the units they have used for x-axis are seconds. Okay, seconds with 10 intervals, 10-second intervals.
Oh, okay. So
Yes,
if
10-second
I
intervals, meaning we will record 6 times in 1 minute, because there are 60 seconds. So if we are recording, okay, with 10 seconds interval, so 6 times in 1 minute. Okay, move on.
okay, so um so if this is for the concentrated hydrochloric acid, and this is the dilute hydrochloric acid, you can see that the concentrated hydrochloric acid ends the reaction with the concentrated hydrochloric acid ends before the dilute hydrochloric acid. This one ends here. Okay, so they both ended up with the same amount of volume of hydrogen produced, but the rates of reaction were different. You can see that this one ended first. The time taken was less because over here we have 0, right? And the axis increasing this way. So less time taken for the concentrated hydrochloric acid than for the dilute hydrochloric acid.
Okay, okay, I have a question. For
Yeah.
those of you who have the book with you, take out page 185, look at figure 7.18, and tell me, and I'm gonna show you, wait, yes, I'm gonna show you this. Can you tell me where did the reaction complete? Those of you who don't have the book can look at my screen. So where did the reaction complete in case of C? Where did the reaction complete in case of D? Tell me the answer in time, in seconds. Tell me the time in seconds. At exactly how many seconds, after how many seconds did the reaction C complete? After how many seconds did reaction D complete? Yes. Okay, Sarah. Yes.
In C part, it's 60 seconds.
Okay. Are you sure? Look,
It's a little behind 60, like 68. No, 58.
60, you mean 58, right?
Yes.
Yes. You know what's the best way of finding this out? Do you know what the best way is? Oh, I wish
No.
I had a ruler. Keep a ruler. Keep a ruler, like, the way I'm keeping my finger, and
Yes.
look at where the graph is leaving the ruler. Where
Isn't it
where is
isn't
Sundus,
it 56?
can you bring your ruler here real quick to me? Look at where the line is leaving the ruler. That point, follow that point and draw a vertical line all the way joining the x-axis and C. Okay?
Yes, that's 58.
Jazakallah khairan. Jazakallah khairan. Okay, so this is the ruler. Why does it blurred out? Yes. So where is it leaving my ruler? Yes, it is 58 or 56. Yes, 58. I think 58 is safer. It is safer to say 58 than 56. Okay, now let's talk about reaction D. Why is my camera blurred? Where is it? Or you can just see where is the blue line separating from the red line. Where is it separating? Here. Okay, who will tell me? Muhammad. Yes, Muhammad.
Yes, ma'am. Can you show the graph? Yeah,
Sorry?
it's 115 maybe because I don't have the book.
Okay, it is 100 and what? 16 you said?
13 maybe, or 15.
13. So this is 112 and this is 114. So you're saying in between. Yeah, you can say that. Yeah, to be on the safe side, I think it's 114, but yeah, 113 is also acceptable. Yeah, 114, right? So how did you, I mean, what point did you see to decide that the reaction has stopped?
Where the line was being horizontal,
Why should the line be horizontal?
because no more products were made.
Yes, that means the volume of hydrogen is no longer increasing, meaning whatever hydrogen had to be produced is now produced. That's it. No more hydrogen being produced. So time is going on, but no more hydrogen is being produced. Time is going on, but no more hydrogen is being produced. So can you see that this completed at 58 seconds and this completed at 114 seconds, let's say. So that's like almost double the amount, double the time period, right? So that, and why was the time period doubled? Because the concentration was halved. Can you see? So you can say that concentration is inversely proportional to the rate of reaction, or inversely, no, sorry, concentration is inversely proportional to the time the reaction takes, not rate. With rate, it is directly proportional. More the concentration, more the rate of reaction, right? But it is inversely proportional to the time that the total reaction takes, right? Okay, okay. Now let's move on, Sundus. Are we done?
Yeah, for concentration.
Okay, let's move on to temperature.
Okay. So,
So first explain the effect of temperature on the rate of reaction using the kinetic theory of matter.
yeah.
Number of collisions and all of that, number of collisions and everything.
So temperature, as you know, is the average kinetic energy of all the molecules. So,
Right.
uh, by kinetic energy, we know it's the energy of motion. So the faster the particles are moving, the higher the temperature is. So the faster the particles are moving, the more chance there is of there being a successful collision. And higher the chance of successful collision, more the reactivity, right? So the increase in temperature means an increase in the rate of reaction. So for this, to prove this, we're going to use where the experiment that we're going to use is sodium thiosulfate and hydrochloric acid, giving us sodium chloride, sulfur dioxide, and water. So just looking at the reaction, can you tell me the precautions that we should take before we do this experiment?
Yeah,
Nabi,
okay. Keeping the reactants in mind, what
Maruch,
are the precautions? What are the precautions that we should take?
Muhammad?
Yes, Muhammad?
We should wear eyeglasses and gloves.
Yeah, goggles and gloves.
And
Yeah,
look at
why?
the
Because of which reactant? Muhammad, sodium thiosulfate or hydrochloric acid? Which reactant is more dangerous? Yes, Nabil?
Miss,
Yes.
thiosulfate, sodium thiosulfate.
Thiosulfate is more dangerous. Sundus, is he right?
I think hydrochloric acid.
Yeah, I think so too. I think it's hydrochloric acid. Yeah, maybe sodium thiosulfate is also, but hydrochloric acid, it's one of the strongest acids that we come across in the laboratory. So we got to be careful. Okay, if it is splashes or anything, then especially your eyes and your face and even your hands should be all covered and protected.
And
Okay.
also look at the reactants. Something
Yeah,
else.
we were looking at the reactants. Okay, you mean to ask why are we using sodium thiosulfate?
No, I'm saying which other precautions should we take?
Hmm. Okay.
There's
Yes, Ajwa. Yes. Yes.
We should perform the experiment in a fume cupboard because sulfur dioxide is released and it is a toxic gas.
Yes. Good. Yes. But Sundus, you were talking about reactants, right? You were asking about the reactants.
Oh no, I meant to say the products. I'm so sorry.
Oh, okay, okay. So is Ajwa's answer correct?
Yeah, exactly correct.
Yes. Yes. Okay. So another thing, my question, I have another question. Of all the reactions, why did we choose this one to study the effect of temperature on the rate of reaction? Y- Yes, Nabil. Yes, Nabil.
Miss, can you repeat the question?
I'm asking why did we choose this reaction to study the effect of temperature on the rate of reaction?
Due to this is the reaction which we can study of kinetic theory of molecules, as this reaction takes place of a kinetic theory more than any others.
No, all the reactions follow the kinetic theory, all of them. Okay, Sundus. Okay, Maruj. Yes.
Isn't it just because that if they both react, they will change color depending how much product they are giving?
Yeah, you see, we have to have something to measure. Like, how would we know that the reaction has taken place and how much of it has taken place? Like, we need some parameter to follow, which will help us in which will give us an idea of how much the reaction has proceeded. So this thiosulfate is a colored substance, okay, and it will lose its color as the reaction will proceed. Why? Because thiosulfate is a yellow colored precipitate. It's a yellow precipitate. It's a yellow solid. And as the reaction will proceed, it will lose that color because it will give away. Or Sundus, is it the other way around?
Yeah, that's what I was about to say. I think it's
Oh,
because of
sorry.
the sulfur suspension that
Yes,
it.
sulfur. I'm so sorry. Sulfur is a yellow powder. Okay, sulfur is a yellow powder. And so as the reaction will proceed, you will start seeing the yellow sulfur powder in the form of a precipitate. And I think sodium thiosulfate is a colorless solution.
Yeah.
Yes, okay. So both hydrochloric acid and sodium thiosulfate are colorless reactant solutions. So we will start with a colorless solution, and as the reaction will proceed, you will start seeing yellow precipitate. So it is easier for us to trace the rate of reaction, I mean to follow or to record the rate of reaction, right? And so that is why we chose these reactants. Okay, Sundus, go on because we have a very less time left.
Okay,
So try to complete and finish this experiment. Okay.
so for temperature, we're going to use two flasks. Again, we're going to compare, right? So we're going to keep use one. So we're gonna place hydrochloric acid in conical flasks like this. Okay, so for now, I'm just taking two of them. Okay, and if this one is at room temperature, and if I heat this one up for up to like 40 degrees Celsius, so it's lukewarm. And then I'm going to add sodium thiosulfate in each, and I'm going to start my stopwatch. And below the conical flask, I'm going to keep a paper with a inked cross on it. So you can keep anything. You can even keep a solid colored, you know, a sheet of paper, colored paper, or anything written on a page. So you can also look at the figure in the book 7.19, and that's the real experiment. So we're going to record the time it takes for the cross to disappear, because sulfur, when sulfur is produced by this reaction, it's really fine in small grains, so it stays suspended in the solution and makes it opaque, so you can no more see the cross. So faster the higher the temperature, faster the reaction, faster the cross is going to disappear. Lower the temperature, the longer it's going to take for the cross to get out of sight. So
Yes, and I would recommend that as she's explaining, please look at the pictures on page 186, figure 7.19, those of you who have the book. Okay, Sundus?
so this is the figure that I'm talking about, and you can see that they've placed a paper with a cross, and
Okay,
this.
let me share my video and let me show the picture for those of you who don't have the book. I mean, this is, I think, only Haidu can see yellow powdered sulfur, and because it is denser than the water, therefore it settles at the bottom. And you can see that the black marker is visible here because the reactant is a clear solution, like water, it's transparent. Okay, whereas in this case, because of the sulfur deposition at the bottom, the cross is no longer visible. So we will use the, as the reaction will proceed, you will stop seeing it altogether. Like in this case, you can no longer see the cross. Why? Because the opaque sulfur powder is sitting on it, right? So this is how we will like follow the rate of reaction. So the dimmer the cross gets, we know more and more sulfur is being deposited, is being formed. So the reaction is proceeding forward. Okay. And this is another picture because we're using hydrochloric stopwatch. As soon as we add dilute acid, we start timing. And then we will record how much time did it take for this cross to disappear. As soon as you stop seeing the cross, you click the stopwatch again and you turn it off. As soon as you stop seeing the cross, you turn the stopwatch off, and then you will note down the time that it took for the cross to disappear. Okay, okay, Sundus. And then this is the study tip. It is important to realize in this experiment that the shorter the time taken for the cross to disappear, the faster the reaction has taken place. Because sooner the cross disappears, meaning faster the sulfur is getting deposited. Faster the sulfur is getting deposited, meaning faster the reaction is proceeding forward. Okay, Sundus?
Can you hear me?
Yes, yes, I can.
Because apparently my video is stuck. Can you see it
Okay.
move?
So let me stop my video. Yes.
Okay. Now can you see it?
No, no. Okay, also appreciate the fact that the rate of reaction is inversely proportional to the time the reaction takes. So if a reaction is faster, it will take less time. If the reaction is slower, it will take more time. Okay.
Can you see the
Here,
graph?
here is the equation of the reaction. Let me see. I still cannot see your screen. I cannot see your screen. Okay, are you trying to discuss figure 7.20?
Yeah, at the graph, right?
Yes, or just simply share, show the book.
So I am trying to show the book, but the video is hung.
Okay, so you use my screen to explain. Look at my screen.
I can't see your screen either.
Okay, can others see my screen? Yes, Nabil? Yes?
Yes, I can for 1 minute, but now it's not visible.
I don't know why is this happening.
No, actually, there was a Zoom update in the morning, so I think it's because of that.
Is the time taken for the cross to disappear, and x-axis is the temperature. Because why is the x-axis temperature? Because we are studying the effect of temperature on the rate. So the two parameters we are using are temperature and time for the cross to disappear. Yes, Abdul Rahman, do you want to say something? Yes?
You can try changing the host. Maybe that will work out.
Try changing the host. Okay, let me just explain this real quick because we don't have much time left. Okay, so as the temperature is increasing, what's happening to the time? That means the cross is disappearing faster and faster. Okay, time taken for the cross to disappear is decreasing. So this is an indication that as the temperature is increasing, the rate of reaction is also increasing. And can anybody explain that in terms of the kinetic theory of matter? In the correct sequence, I'll be really happy. Yes, Ibrahim, good job.
Miss, can you repeat the question?
Can you explain the effect of temperature on the rate of reaction using the kinetic theory of matter?
Yes. When the temperature is increased, the kinetic energy of the molecules increase. So there is
Average
more
kinetic
likely,
energy. Average kinetic
yes,
energy
average kinetic energy increases. So that
of the
there
molecule.
are more of the molecules. So there are more chances to collide. More chances for successful collision of molecules.
Yeah, more. Okay, now as you are saying, I am improving. Okay, I am improving
Yes,
on your words. Why am I doing this? This is very important, and I do this all the time with Sundus and with the rest of my kids, because this is that structured answer. They so often ask this question: explain the effect of this factor on the rate of reaction using the kinetic theory of matter. So how will you go it? Yes, you told me the first point absolutely correctly, that as we are increasing the temperature, we are increasing the average kinetic energy of molecules. And so they are colliding more frequently. So what will you talk about? Frequency, and also more violently, or you can say with more energy. Okay, Ibrahim? Yes, Ibrahim, can you please repeat after me? Can you now talk in terms of the increased frequency of collisions and a collision with greater energy? Or did you mute yourself? Okay. Yes, I
yes, miss.
unmuted you.
I muted myself. Yes.
Yes, okay. And then after this, more collisions and more
More collisions.
yes, and
Yes.
more.
More violent collisions and more frequent collisions.
Very good. And more violent collisions with greater energy. Yes.
And
And then?
yes. And then the rate of reaction is
No,
increased.
no, 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 no. You will say that more successful collisions.
More successful
Yes,
collisions
more successful
that
collisions.
result in
More product formed in
yes,
the same time period or in a
less time.
shorter time period. More product in a shorter
Yes.
time period.
Yes.
Right. Okay. So this is very important. Okay. So
Okay, miss.
yes. Okay. So is there any points on this left in this?
No, I don't think so.
Yeah. Okay, the next topic is catalyst, right?
Yeah.
Okay, catalyst, and then there are enzymes. Okay, enzymes are in biology as well. Okay, and then after enzymes, we will start with the past paper questions. We will do past paper questions on this chapter, same chapter, energy, energy of reactions.
What about the photochemical reactions?
Yeah, okay, we will do photochemical reactions as well. Whatever is included in your IGCSE syllabus. Okay.
Okay.
So we are left with enzymes, catalysts, and then we will do the past paper questions, and we will also, inshallah, do these experiments in the CD. You know, these activities, like for example, this activity 7.5, the effect of concentration on the rate of reaction. Okay, inshallah, after the catalysts and enzymes. Okay, then take care. Assalamu alaikum wa rahmatullahi wa barakatuh.
Allah Hafiz.
Allah Hafiz. And this is stop the recording.
Yeah.